Hello students, this is Professor Chalai, and in this video we're going to look at the heat transfer between substances. As always, you can follow along with our Chapter 5 workbook. By the end of this video, you should be able to explain the process of calorimetry and also calculate heat transfers in thermal equilibrium problems, which we'll get to. But before we get to that, let's do a quick review of heat. We learned in our previous videos that the heat is a measure of can be measured from temperature changes in materials. So for example, the heat will be some constant times the temperature change in the material, where that temperature change, delta T, is going to be the final temperature, the temperature that it ends at, minus the initial temperature, the temperature it started with. If you're dealing with specific kinds of materials, that heat will be related to the mass of the material, so that heat will actually be equal to the mass of the material times the specific heat capacity, Cs, times the temperature change. And that equation is what we're going to be using a lot. All right, so with that refresher out of the way, let's look at heat flow. Because in all setups that we're dealing with, the heat that something gains must have come from somewhere, or if something loses heat, that heat must go somewhere. And so if we divide our setup into two parts, the system and the environment, where the system is the part of the setup that you're interested in, and the environment is everything else around it, then the heat that the system gains must come from the heat that the environment lost. And so that's why we have the heat of the system, Q of the system, is equal to negative the Q of the environment. This also means that if the system lost heat energy, the environment would have gained heat energy. That's all this means. It doesn't matter where you put the negative sign, so you could have simply written the negative, the heat of the system, is equal to the positive, the heat from the environment. Both are exactly the same mathematically. I just choose to write it this way. So always remember, heat must come from somewhere or go somewhere, and so the heat from the system is negative the heat from the environment. All right, so the way we go about measuring heat flows in chemistry is by using a setup called a calorimeter. So a calorimeter is just any device used to measure the amount of heat in a chemical or physical process. And the simplest type of calorimeters is this coffee cup calorimeter here. All this is a styrofoam cup, right? This is our styrofoam cup, and usually styrofoam or any sort of insulating material, because it doesn't let heat escape out into the atmosphere, but it keeps all of the heat inside of the cup. And so you'll perform a reaction inside of that cup with some water in there, and you'll have a temperature to measure the temperature change of the water, and you'll have a stirrer to just mix the water up and distribute the heat evenly. So what would happen is, if you're running a reaction in there, the heat from the reaction, if the reaction lost heat energy, then that will go into the heat of the water. Sometimes we just call this the water the calorimeter. So that's it. So if a reaction lost heat, it will go into the water. If a reaction gained heat, it will go in. If a reaction gains heat, would have come from the water, and the water will reduce in temperature. If the reaction lost heat, the water will gain that heat and it will go up in temperature. So the reaction would be the system, or the part of the setup that we're interested in, whereas the water or the calorimeter will be the environment. That's water. So that's a simple coffee cup calorimeter. You can make this in a lab easily. All you need is a thermometer, a coffee cup with a lid, some water, and your reaction goes in there. All right. So whenever you have a setup like this, where two things, the water and the reaction, are in contact with each other, and they could lose and gain heat to each other, eventually, after a while, they will come to what we call thermal equilibrium. That's where their temperatures are going to be the same, and so heat can no longer flow between them. So thermal equilibrium is the condition when the temperatures of two substances are the same and heat will not flow between them. Thermal equilibrium. So all pairs of substances, if you keep them in contact with each other, eventually, if you leave them for long enough, eventually will come to thermal equilibrium. All right, I'll do one practice thermal equilibrium problem in this video, and I'll do the rest in the other video to keep these videos short. Hopefully they're kept short. So let's look at number 5. In number 5, we have two substances, and let's identify them. We have an aluminum and water, right? The aluminum starts out at, we have 32.5 grams of aluminum starting out at 45.8 degrees Celsius, and they give us the specific heat capacity of aluminum right there. For water, we have 105.3 grams starting out at 15.4 degrees Celsius, and they also give us the specific heat capacity. So looking at this, we have aluminum at 45.8 degrees Celsius, so that's pretty hot. Water at 15.4 degrees Celsius, that's sort of a little bit cold water. If they go into thermal equilibrium, their final temperatures should be somewhere in between those two, right? It can't be colder than the coldest thing you started with. It can't be hotter than the hottest thing you started with. The final temperature would be somewhere in between, and they're asking us, what is this final temperature? So let's write this problem and try to figure out how we might solve for the final temperature. So this is a heat flow problem where heat is going to flow from one part of the setup to another. So let's start with this Q of the system is Q of the environment. We just need to choose which one, aluminum or water, is our system, and which one, aluminum or water, is our environment. It doesn't really matter which one you pick. The answer should come out to be the same, but we'll choose aluminum as the system, water as the environment. So Q for aluminum should be negative Q for water. Okay, that's good, but let's expand that. They give us the mass, the temperature, initial temperature, and the specific heat capacity. So you bet we can use for Q the specific heat capacity equation that we already looked at, where the Q should be the mass, the specific heat capacity, and the temperature change. So let's do that. So the Q for aluminum will actually be the mass of aluminum. So let's just put symbols for now. We'll put in numbers later on. So it's the mass of aluminum times the specific heat capacity of aluminum times the temperature change of aluminum. So yeah, let's do for temperature change. We need to find the final temperature, so we don't actually know what the temperature change is. So I'm going to write final temperature minus initial temperature of aluminum. Right? So that's the heat for aluminum. I expanded that out. The other side of the equation will have negative the heat for the water, which we can also expand out. So we'll have negative the mass of the water times the specific heat capacity of water times the temperature change, which again will be the final temperature minus the initial temperature of water. Note that the final temperature in both situations would be the same. So in this setup, if we examine this, we know that we have the mass of aluminum, it's right here. We have the specific heat capacity of aluminum, right? It's given right here, or you could look it up in a table. We have the initial temperature of aluminum, it's right here. We don't know the final temperature. On the right-hand side of the equation, we have the mass of water, we have the specific heat capacity of water, and the initial temperature of water. We don't know the final temperature. But because this is in thermal equilibrium, the two final temperatures are identical. So that's why I kept them in the same color. Okay. So all this means is that we need to do some algebra to solve for TF in this equation, because everything else we know the value of. Now, what you could do at this point is just start plugging in numbers and solving for TF. But I'm just going to rewrite this equation to solve for TF my own way, because why not? So to do that, I'm going to keep all of the things. I'm going to first expand the equations out. So let's do that. So mass of aluminum times the specific heat capacity of aluminum times TF. So we'll have mass of aluminum times the specific heat capacity of aluminum times the final temperature. And then we'll have minus the mass of aluminum, the specific heat capacity of aluminum, and the initial temperature. So minus, let's go back to orange, the mass of aluminum times the specific heat capacity of aluminum times the initial temperature of aluminum. So all I did was expand out this bracket to make my life easier. I mean, it seems more complicated now, but this is the way I'm going to go about solving this problem. You can solve it by just plugging in the numbers in this step and try to solve for TF. Either way should be correct. I find that this way just makes it simpler to keep track of significant figures. Okay, here we should have minus the mass of water times the specific heat capacity of water times TF. So minus MH2O times specific heat capacity of water times TF. And then we have minus water times specific heat capacity times minus Ti, so that all becomes plus, right? Minus and minus becomes plus mass of water times specific heat capacity of water times Ti, the initial temperature of water. Okay, so now our unknowns are TF and everything else is known. So let's keep everything with TF on one side of the equation. I'll put them on the left-hand side, and then I'll put everything else on the right-hand side. So I'm going to add this to both sides of the equation. So I'll get this guy, mass of aluminum times specific heat capacity of aluminum times TF minus added to this guy. So that will be plus mass of water times specific heat capacity of water times TF. So I moved all that to the left-hand side. And then I'm going to move this to the right-hand side by adding it on both sides. So that will give us this guy again is equal to mass of water times specific heat capacity of water times the initial temperature of water plus this guy. So that'll be plus mass of aluminum times specific heat capacity of aluminum times the initial temperature of aluminum. I know this seems like a lot of work, but we can simplify this even further. So here we have TF and here we have TF, so we can simplify this into TF multiplied by this guy right here. So that's mass of aluminum times specific heat capacity of aluminum time plus, I shouldn't have closed the brackets, plus this guy, mass of water times specific heat capacity of water, close brackets. So I just simplify that. And then on the right hand side, we have this this guy repeated. So I'm not going to write it again. Let's see if I can just drag this down. There we go. Okay. So now to solve for TF, we just need to divide on both sides by everything in this bracket. So the beauty of doing this electronically is I should be able to select this. I didn't select everything. Let's try that again. Select this and divide both sides. So TF is equal to all of that. So now I have all of the unknowns on the left, all of the knowns on the right. These are all numbers that I can plug into a calculator. So let's write them out. Mass of water is 105.3 grams. CS of water is 4.18 joules per gram per degree Celsius. Initial temperature of water was 15.4 degrees Celsius. All of that added to mass of aluminum, which was 32.5 grams, times the specific heat capacity of aluminum, which was 0.903 joules per gram per degree Celsius, times the initial temperature of aluminum, which is 45.8 degrees Celsius. Already you can see grams will cancel out with grams, degrees Celsius cancel out with degrees Celsius. Similar here. That's the numerator, and then in the denominator, we have mass of aluminum times the specific heat capacity of aluminum. So mass of aluminum, 32.5 grams, times the specific heat capacity of aluminum, 0.903 joules per gram per degree Celsius, plus the mass of water, 105.3 grams, times the specific heat capacity of water, 4.18 joules per gram per degree Celsius. So grams will cancel out in both of these examples. All right, let's solve for the top first, the numerator. So 105.3 times 4.18 times 15 gives us 6778 joules, but to 3 sig figs, that's 6780 joules. And then this part gives us positive 1344 joules. To 3 sig figs, that's 1340 joules. In the denominator, we get 32.5 times 0.903, which is 29.3 joules per degree Celsius, plus 105.3 times 14.18, which gives us 440 to 3 sig figs joules per degree Celsius. All right, now things are getting even simpler. 6780 plus 1340, that's 8120 joules. On the bottom, we have 29.3 plus 440, that's 469 joules per degree Celsius. And now finally, we divide 8120 by 469 joules per degree Celsius. The joules cancel out, and so our answer will just be in degrees Celsius, right? You're dividing by 1 over degree Celsius. And that gives us 17.3 to 3 sig figs degrees Celsius. That's our final temperature. All right, that seems like a lot of work, and it was, but we got there eventually. So let's see if 17.3 degrees Celsius made sense. We said that it's going to be somewhere between the lowest temperature and the highest temperature. The lowest was 15.4, the highest was 45.8. 17.3 is between those two. So seems like the final answer is correct. You might be asking, why isn't it somewhere halfway between the two? Why is it so close to the lowest temperature? Well, for a couple of reasons. One, the specific heat capacity of water is so large compared to the specific heat capacity of aluminum, right? It means that it takes a lot more heat to heat up water than aluminum would have lost to cool down. When aluminum cools down, it releases less energy compared to what it would take for water to heat up. And the second reason is we have a lot more water than we have aluminum. So the amount of water that we have is a lot. So it makes sense that the final temperature is closer to what the water started out at. I hope this all makes sense. It's a lot of algebra, and there are a lot of ways to solve algebra problems. I did a pretty long way by solving for the final temperature symbolically first and then punching in all the numbers. So then when we get to this stage, it's all punching in numbers and keeping track of sig figs. Or you could have just started punching in the numbers once you set up this equation right up here. You could have started punching numbers in there and then work your way out to solving TF. There's no correct way as long as you got to the same answer and you got to the same correct number of significant figures. All right, with that, you have all of the tools you need to solve questions 6, 7, 8, and 9. They're all heat flow problems where the two substances are going to be in thermal equilibrium in the end. The setups are going to be the same as we did here. We're going to start with the heat flow equation where the heat for the system is negative the heat for the environment, and then you're going to expand out and then solve for the one unknown that the problem asks for. If you have questions, please let me know. In the next video, I'm going to go over those problems, and I'm just going to speed them up because you probably don't want to hear me talk about go into detail about how I solve each and every one of them when it's just mostly algebra. All right, so try those, and when you're done, look at the next video to see if you got the correct answers. I'll see you in the next video.